In today's lesson, we're going to understand thermodynamics. We'll explore the four processes, we'll find the work done by a gas, and we'll be able to calculate the efficiency of an engine. So the first thing you need to know about a thermodynamic system is so you can draw a boundary. Work or heat can be transferred across the boundary. Everything outside this boundary is the surroundings. So we will have something here, and everything outside is the surroundings. And we'll be doing work and heat in an isolated system. So there'll be energy being used and things will be happening. So we have three types of systems. We will have a closed system where matter, particles, cannot move across the boundary, but energy can. You can have an isolated system where everything is blocked off, and that means that energy or matter cannot move across the system, or the boundary, I should say. We have an open system where energy and matter can leave the system. So these are three main types that we need to know about. You have three major words that you need to understand: the internal energy, the heat, and the temperature, or even work as well. Essentially, the internal energy is all the energy inside a substance, the full energy. This energy can be a combination of heat and temperature. Heat is the internal energy that will be transferred from one object to another, or one object into the surroundings. So when something gets hot, you can feel the heat escaping. Temperature is a measure of the kinetic energy of the particles. We did this in the previous lesson. Temperature is how fast the particles are moving. More speed of the movements, the more temperature we will have. There are four main processes. The first one is isobaric, which is constant pressure. The next one will be isothermal, constant temperature. Isovolumetric, constant volume. And adiabatic, or adiabatic I should say, said that wrong, adiabatic, constant heat. So here's a little table that will help us figure out whatever we need to find. So isobaric, constant pressure, the pressure will be 0. So if you wanted to find the energy, it's a combination of the heat plus the work done. If we were to have a graph, it would be a horizontal line. So isobaric, if you've seen a little graph, if you had a straight line going along the way, this would be isobaric. The pressure is not changing. Isothermal, constant temperature, the total energy will be 0. The heat will be the same as the work done. The temperature did not increase. This will be a rectangular hyperbola, which is this little curved thing. This would be isothermal. So if you see this in a graph, you know it is isothermal. Isovolumetric means the volume doesn't change. So the work done will be 0, because if you know what work is pressure times volume, which we'll talk about very soon. The work done will be 0. So the energy, all of the energy, will simply be the heat. And that would be a vertical line going like this. So if it's got a vertical line, this is isovolumetric. Adiabatic is when there is no heat entering or leaving the system. So the heat was 0. Whatever my internal energy will simply be the work done. Okay, that's a steep hyperbola, which is like a much steeper line going like this. It's going something like that. Okay. Work done by a gas in a piston at constant pressure. You can find the work done simply by doing the pressure multiplied by the change in volume. A process at constant pressure is called, if you remember, isobaric. So to find the work done, we will do the pressure times by the change in volume. So it's two volumes. We have a final and a starting volume. So we'll put that into our formula. We have 1.1 pascals multiplied by 2.5 minus 3. You will get negative 0.55 joules. It is negative because work is done on the gas. So that's important to know the difference between positive and negative work. Work done by the gas or by the system will increase the volume, and that means it will do positive work. Work done on the system to compress or make the volume smaller, it will be a smaller volume obviously, and the negative work will be done. If there is no change in volume, there is no work done. Just like what we did in term 1 when we talked about force and displacement. Without a displacement, there is no work. And here, the volume, change in volume is the displacement. If there is no change in volume, there is no work done. So, how is energy exchanged between the system and its surroundings? Well, you can add or remove heat. Remember, we used heat or Q, or even EH. Both are the same. This is energy, which is heat in this case. You can do work, expansion or compression. This is another way to exchange energy. Both of them result in a change of internal energy of the system. This leads us to the first law of thermodynamics that we need to know. The change in the internal energy in a closed system is equal to the amount of heat supplied minus the work done. In an isolated system, you cannot have more energy or less energy than we started with. Whatever the heat we used minus the work will be the change in energy. The total energy will be zero. This is the conservation of energy. Total energy remains the same. Whatever the heat is, it must be whatever the work will be done. Here's an example. In an isothermal process, 50 joules of work is done. How much heat was used? So here is a little table to help us remember. Isothermal process, we know that it will be Q is the same as negative W. Let's see if we get that right. So U is Q plus W, the general rule. We have total of 0 energy at Q plus 50, which means if you wanted to find Q, you will subtract 50 on both sides. You will get negative 50 joules, which makes sense. It's the opposite of the work done. So a reminder, first law of thermodynamics, total energy is the heat minus the work done by the gas. Okay, so the work done by the gas is opposite of the work done on the gas, so that will become negative. You can also find the work done if you have the graph. You can just find the area under the PV graph. And if it's done by the environment, it'll be a negative of that. So for example, here is a pressure, we have a volume, we can do P times V, these are the two volumes, just like we did, we can find the area under the graph. Sometimes you might get a triangle, it might be looking like this. That's not a problem. What we can do is the area of the triangle, which is a half times that. So a half times the base times the height. And just a reminder, if you see a straight line, work done will be 0. No need to calculate anything. That takes us to heat engines. The final part of this lesson is a heat engine. What is this? So it's a device that takes energy from a hot reservoir and it pumps into the engine. The engine will do some work and it will move something. The remainder of the energy goes into the cold reservoir at the end. So heat will be expelled and it'll be a lower temperature. You can do a quick calculation to find the efficiency, how good this engine is. The the efficiency is the work over the energy that I brought in, the heat that I brought in. The work done, of course, will be the Q hot minus the Q cold, whatever I had over here, minus whatever I've used, divided by what I put into it in total. This will give me an efficiency. You can times by 100 to make it into a percentage. Here's an example. An internal combustion engine, it produces 300 kilojoules of energy. Kilo means 1,000, remember? But it uses 500 kilojoules of energy in the process. What is the efficiency? We can use the formula, work divided by Q hot. We'll subtract the two numbers, 500 minus 300, big minus small, divided by 500, which was the heat that came in, multiplied by 100 to make that percentage I was mentioning. So if you were to do that, you would get 40% of this efficiency. Very nice.